Rocking it in 3D, 3D, 3D. Okay, so what we're going to look at here is adding vectors in their components up together, but we're going to do it in 3 dimensions this time. Last time when we did this, we saw that if we're adding things together, either for x's and y's or i's and j's for unit vectors, we simply actually just look at the i's and j's and add them together in their columns. And if we had a third vector, or a third, dimension, if we had a third dimension to make it in 3D, like the z-axis or the k-hat direction, we would just add these up together, okay? In our case here, what we're going to be looking at is what is actually the displacement vector d from jet B to A. And to actually solve this displacement vector, we want to subtract these values. So we actually want to take A minus B, and this here is going to give us our answer. It's going to give us our displacement vector. Now to do this, you do the exact same thing as before, except watch for this negative. Let's add our i's together. So we're going to have negative 250 minus 125. So that's going to give me negative 375 in the I hat direction. Okay, this looks pretty straightforward. For my j's, I'm going to have 620 minus negative, so minus the negative, that's like adding. So 620 plus 240, that's going to be plus 860 j hat. And then 740 k hat minus 319, and that's going to give me a plus 421 k hat direction. And this will all be in meters because that's my unit, so I'll put a little parentheses around it so I can say that meters are everywhere. Okay? And that's how we do that. We did it in 3 dimensions because we have an x, y, and a z direction because our world is in 3 dimensions. And we simply just, look at what do you have in these columns with a little bit of careful being played out to the front. Okay? So nothing crazy there. If you actually wanted to, though, figure out this d vector, that is the d vector that points from B to A. If you wanted to figure out what distance that actually was, if you wanted to find out that actual distance, then you could do a 3-dimensional Pythagorean theorem. And it sounds more complicated than it is, because on a normal Pythagorean theorem, you just take whatever your x quantity is squared and you add it to your y quantity is squared, and this gives you the hypotenuse of your triangle. If you want to do this in 3D, you simply take the square root of your x quantity squared plus your y quantity squared plus your z quantity squared, and that gives you the hypotenuse of a 3-dimensional triangle. It's not exactly a hypotenuse thing, so it's kind of a 2D object, but this is actually just some distance vector. And if you actually remember back in your math classes, while we could call this the hypotenuse, they'll also call that in math classes a distance vector, or a distance as well, or how far apart things are from one another. So very similar there. This is just how you kind of do a 3-dimensional Pythagorean theorem or an edge of a triangle. Nothing really changes. Nothing gets more complicated. But that's what's going on here. Okay, so whenever you're trying to add up vectors together, add up the x's, add up the y's, add up the z's, or the I, j's, and k's, and you have your vector. If you need to find the actual length of that vector, just take a very large Pythagorean theorem, and that's it. Okay? So I hope you enjoyed that. I hope you got something out of it. But that right there is finished. We've just added up vectors in both x, y's, and z's. In our next video, we're going to go back to the boat, and we're going to look at relative velocities, or how do people view objects that are moving under 2 vectors. But until then, adios, and take it easy.